benchmark for the peak efficiency, and then looking at practical results compared to that is a relatively new concept. What is there to do next? Well, you can do exactly all the same stuff as that I've done, but do it in elliptical cylindrical coordinates if you're a math boffin. So yeah, I kind of looked at doing that and shied away from it because it was just quite difficult. There's definitely an ability to develop a body of data to examine radiation efficiency. So if somebody can sort of take the basic idea and go out and plug sort of 15 different bodies up and down in the water and measure their waves, you can start to get a pattern of going, okay, well this is good, this characteristic's not so good, and kind of working through a bit of a selection process. Wave breaking in circular waves, whether the early wave breaking in the cylinder sphere was caused by the sphere body itself, or just that circular waves break earlier than regular waves, would be a great question to answer. Knowing what's causing that breaking will help you understand how you can get a more efficient conservative wick. And also power absorption factors. You can also determine power absorption factors based on characteristic cylinders. So this is actually something I've started with. So the characteristic cylinder theory has been mainly worked on looking at radiated waves. You can, in theory, also introduce a plane wave and look at the displaced volume of the two of them together. And then you can calculate things like absorbed power, your absorption length. So we talked about that earlier, absorbing more energy than is incident on the device. You can actually relate the radius of your device to your absorption length and find out theoretical limits. And that work's already underway. And then, of course, is applying all of this understanding to wave energy converters. And there's definitely some scope for that. So going back to this Laplace, if you notice what happens as it plunges down there in the first instant, what you get is a massive wave breaking right at the front. And so in terms of conservative theory, which the Laplace wasn't designed around, but in terms of conservative theory, it's limiting its power efficiency by the simple fact that it causes such a large breaking wave in front of it. Any further questions?
Yeah, we've got about 12 minutes still. Please be like presentations.
In several cases, you mentioned there's obviously a turbulence effect in this case, but during any of your experiments, did you try to calculate what the Reynolds number is on the surface as a way of characterizing for future work the effect of the turbulence on the surface?
No, I haven't. It just hasn't been done. So calculating the Reynolds number ends up being I found it relatively challenging for, it's an oscillating body. So your actual fluid flow around it, the speed of fluid flow changes as you move through the motion, so you can't apply steady flow theory to it. So I shied away and limited the scope of the project from that.
Where in the model, so there was a slide we presented when you were talking about the helium sphere, yes, and you presented the experimental results and the model results.
Yep.
And they were in quite good agreement. I'm a little confused as to where in the model does the geometry of the device plug in?
So the model is just looking at waves. So the geometry of the device doesn't affect the model of the waves. So this was just looking at the model of the form of the waves and matching it to the data.
Okay.
So yeah, it doesn't look at the geometry of the waves, and that's slightly different from what modern theory does. But then the math ends up being significantly simpler because you don't need to go into quotient functions and look at distributed points along the surface of the body. If you just look at the waves themselves, that sort of gives you the indication that the models match or not.
So what I'm kind of trying to get at there is that I'm trying to get a sense of when you're considering different shapes.
Yep.
Is it important? Does it matter? Well, for a cylinder, for example, the displacement the water displacement is proportional to the linear position, the linear displacement, right? If you put it twice as far in, it moves twice as much water out,
Yep.
right? But obviously not true with something that's conical or spherical,
Correct.
right? Is that important? Does that matter? That non-linearity, you know?
In fact, the non-linearity works out to be sort of quite useful. And actually, sort of one of the things I'm working on is looking at displaced water with depth profile, and it turns out that a linear cylinder is not actually what you want anyway. Still working on that, so I haven't got the end result. But the idea of the characteristic cylinder is that it compensates for that. So if you have something that flares greater, you end up with a squatter characteristic cylinder than you do with something which is just sort of mildly flared or circular. And so in terms of calculating efficiency, you can account for that with this theoretical maximum. Whether it makes a difference in terms of wave radiation, I think it definitely does. I think if you're flared out too far, you're going to get a lot of wave breaking very early in the process. And also if you're quite flared, you limit how far you can move up and down. So there are practical implications of exactly that, but in terms of the theoretical stuff, the idea of a characteristic cylinder takes care of that.
So let me ask you sort of a related question. So if you have a shape and you're moving up and down via the nice test that they had, so clearly visually you can see that there's a wave propagating out of that, and it's dominantly one frequency.
Yep.
It's the frequency at which you move this up and down. But will a cylinder versus a sphere, will there be harmonics that are generated?
Yes, definitely.
And are those harmonics different for the different shapes?
Yes.
And so kind of when I say when I'm thinking of something conical or spherical, like as you push it down into water, like the shape of the wave that it makes is maybe not sinusoidal, so there's other harmonics present. You kind of see what I'm saying?
Yes,
Is that true?
Yes, definitely.
Okay, so the shape, so different shapes there'll be different harmonics present in the
Yes.
radiated wave. Okay.
Yep. So I did notice on this heaving cylinder, for the waves that could be measured, there was pretty much only one harmonic.
Oh, okay.
It was all the fundamental harmonic.
Oh, okay.
For the sphere, when you actually calculate the displaced volume of the sphere, there's a fundamental harmonic and a third harmonic of displaced volume. But what you see practically is that you end up with more in the second harmonic than you'd expect based on the displaced volume. And that's yet to be explained, but you definitely see those harmonics present. So, yeah.
Wouldn't you, I'm sorry, I don't mean to dominate it. Wouldn't you expect that would decrease the effectiveness of the device as a wave energy converter? Because everything that you're sending out like other harmonics.
There's a loss.
Yeah, right.
Yep. But that's not to say theoretically the cylinder is perfect. But practically is where it breaks down. And that's where you see when you get a deep water cylinder where you've got all this turbulence coming up and dissipating the energy that you would hope to radiate.
Yeah, and also, Dr. Brecken, there's some work done at the University of Rhode Island by Stephen Grilly, where it's basically, you have a heating cylinder that is dominated by the first harmonic, like you're saying, but he attached several different cylinders of different lengths and different diameters all into one device, and increased the broadband response of the buoy. So when you put it into a real sea, where you have changing wave conditions, then the broadband response is more important.
Did your work play into the shape revisions on the design?
Yes, sort of in and about. Like the reason why they tried the circular flow was to maximise displaced volume. So looking at that displaced volume, and just looked at the curves and went, right, okay, well, obviously the more displaced volume you get, the better theoretically you can be. And so that's what drove them towards that shape, because as it rotates through the goalposts, that's the biggest volume you can get. And also, it's also, in terms of wave breaking, the wedge shape that they had previously just broke waves in every direction. And so it was a consideration. There was credit to Lan and Alistair. It was they had good, robust conversations about this, but then they kind of went, well, that's theory. What are we actually going to do? And kind of work through that. So, yeah.
Any other questions?
So, did you ever, so you're taking your sphere and you're evaluating it as some, equivalent cylinder?
Yep.
Did you ever make a cylinder that was equivalent to your sphere and test it to see if?
No. Unfortunately, with the way things went, that bit of theory was developed after I'd done my experimental bit. Now that I know that and now I have the idea, I'd love to go back and do it, but time's being time.
So is one conclusion of your work that no one should ever use a cylinder for this, for wave energy conversion?
I would say that my conclusion is that a cylinder is not a good conservative wave energy device. So if you're looking at using a cylinder, I'd look at more your flow around the cylinder than looking at your radiated wave. The other thing is that this looks at tall, slender cylinders, and it may be different for shallower, wider cylinders. So, yes and no. I really wouldn't recommend a tall, slender cylinder because even as a surging device, you get too much of that self-circulation. There's no build-up on the front face as you're surging backwards and forwards. So, yeah, really I would be looking more at the changing the cylinder in some way so that it interacts with the particle flow rather than trying to make it a conservative device.
I think the other thing there too is that typically when you have a heaving cylindrical wave energy converter, it's the relative motion between a spar and a buoy. And then the float is driven by the surface displacement of the wave, and the spar, since it's a long skinny cylinder, stays relatively still. And it's also a tension mode or spread mode or something. There's other reasons why it stays still and the float moves.
Yeah.
So it's not a definitive answer.
Yeah. The spar also the spar also is not a good wave radiator. If you look at the cross-sectional area through the surface of the water, it's actually very small. So what you end up is you actually get, as it moves up and down, most of the displaced volume is across the area of the bottom of the goalposts, and it just circulates. So as you move up, the water at the top moves to the water down below. So you're not actually displacing, not generating a wave that way, just generating friction, which is why the spar works so well as an inertial reference. And the fact that it weighs 4 tons or whatever it is.